Well, as I anticipated, the paper that I submitted to Nature Physics Communications eventually got rejected. It got rejected, I think, for a variety of reasons that I'll get into during the course of this video. But yeah, I was anticipating this to happen, and this is one of the major problems with quantum gravity. I think it forces us to think in transplackian terms, in terms of energy, in terms of forces and joules, and yeah, the amount of energy that can be exchanged between two objects. It forces us to take a drastically different approach to, um, well, fundamental physics that is transplanckian, that goes beyond Planck's constant of about, what is it, 6.67 times 10 to the minus 37 or something joules is the Planck energy. And the sorts of energies that I was dealing with in these calculations were 1.86 times 10 to the minus 62 Newton meters. And Newton meter is, of course, equivalent to joules. So, yeah, we're dealing with the transplanckian world in quantum gravity. And I set up an experiment. I set up an experiment to sort of test this hypothesis of two hydrogen atoms contained in a sealed 1 centimeter cubed container at a Lagrange point, and trying to think about that thought experiment, or possibly even a real experiment if we can do that at a Lagrange point in any point in the future, to try and probe physics that goes beyond quantum mechanics, basically. This is really the sorts of problems that I was encountering, and I think it's probably why the paper got rejected, because it's one thing for people to say general relativity is wrong. On a level, we all know general relativity is wrong. We know it doesn't account for dark matter. We know it doesn't account for dark energy. We know it doesn't sit correctly with quantum mechanics. But then with quantum mechanics, we're just in a bewildering different universe of superpositions and particles tunneling and entanglements and all these sorts of things. And it's famously highly counterintuitive stuff, quantum mechanics. But if that stuff turns out to be wrong, well, then where are we? What do we have then to fix upon to say that is correct? The only real thing that we can do thereafter is to go back to classical physics and back to statistical mechanics, which is really what I'm trying to do in this sort of work. And it was a shame it got rejected. I knew it would be too much. Well, it is too much for them, really, at Nature Communications. And so on. I knew they'd reject it, but for the reasons I've outlined, because it is transplanckian, it's yeah, these are smaller numbers than quantum mechanics deals with, really, ever. And what do I really want to say about this? Well, this is the issue. It would have been important to publish anyway. I think it would have been an important thing to publish in any case, because it takes an interesting thought experiment, I think. This idea of two hydrogen atoms in this container and measuring the gravity between two atoms, and the gravity by Newton's law between two atoms is minute, very, very tiny indeed. And but then they say, oh, via quantum mechanics, that's a nonsensical amount of action. That's a nonsensical amount of work, energy, whatever you want to call it. That, well, in real reality, it might not be. And frankly, quantum theory, damn it, might be incorrect. Or important elements of quantum theory also might be incorrect. And maybe in physics we're just stumbling around in the dark more than we think we are. And we think we have this, we're greatly enlightened. We think we're greatly enlightened about the world, but actually perhaps we're not. And I don't know how else to approach this issue of quantum gravity other than by starting with something that's very reliable that we have from classical physics, Newton's law of gravity, because that was, after all, Einstein's starting point, and Maxwell's equations. He started with those two things and sort of put those together and got general relativity and special relativity out of it, and also was one of the founding fathers of quantum theory. But yeah, Planck's constant being violated, transplackian physics, and there's all sorts of other transplackian issues that may be at stake here, such as, well, I mean, this is also really what string theory does, which is another reason why I think it's unfair that the paper got rejected. They talk about dimensions being bound up really, really tight into such small spaces we can't see them, and those spaces are smaller than Planck lengths, I think, are they not? Or they're like 10 to the minus 100 centimeters or something silly like that. And yeah, I don't think my research would have been the first research to ever go transplackian, most certainly not. But out of this, how do we resolve something that's sensible? I think really all I was trying to show in my research paper was that using a set of new assumptions, the force of gravity can be shown to be equivalent to the force of electromagnetism. That we get this idea of a cloud of electrons accounting for the gravitational field of an atom. We then calculate the strength of that gravitational field, and it comes out as 2.216 times 10 to the minus 68 Newton meters cubed per coulomb squared. So 2.216 times 10 to the minus 68 joules of energy, force. That's not a lot, that's really tiny. But that's gravity for you folks. Quantum mechanics and gravity do not sit well together. This is the essence of the problem, And they're saying, oh, it's transplackian, it must be wrong hence. Well, actually, it is not wrong, because I did the calculations for Newton's law, and that's what's come out of it. So on a level, you do still just have to accept this as well. Like, I did the calculations several times over, I checked my working, everything. You can check it if you like. And, that is what comes out. It's a hard pill to swallow. It's a bitter pill for them to swallow. They're going to have to revise everything, basically. Revise all physics. It's gone before quantum theory and general relativity and all quantum field theory, the standard model, everything. Not lose too much of it, we'd hope, but who knows what could happen? Who knows what, the next great, leap forward will be, and who knows, we're in the search for new physics, and, well, I think I've given you some new physics, really. New interaction, new gravito-electroweak interaction, which I didn't come up with, I didn't coin the term, but I thought I had briefly, because I didn't see it in other articles which have been published, because I can't read everything. But, yeah. That's what's going on. Energies smaller than Planck energies. Energies smaller than Planck's constant. What do we do then? It comes back to this stuff. Like Coulomb's law, Newton's law, that's what we have to go back to. And then start plugging in quantities into those equations, and then try and make them sensible. And somehow, which I did by invoking the ratio between the force of gravitational attraction and electrical repulsion, and dividing the number of the electrons in the system by it to yield the number of secondary density electrons, and it's rewriting the laws of physics. That turns out to be what we have to do. If you want this theory of quantum gravity that you want so badly, apparently, physics, this is what you need to do. And I don't know who's going to publish it. I really don't. But I'm trying another journal. I'm trying classical and quantum gravity with the Institute of Physics. Maybe they'll publish it. I don't know. But, bye everyone. Love you lot. See you soon.